Hello folks, another day, and I've been sick for the last 3 days, coughing my life away, and I'll probably be doing some coughing during the lecture today, so please excuse that. One thing, just a reminder again, we have a conference in Buenos Aires, Argentina. Let me put that up there. November 10th. So let me go aside here. November 10th, we have a conference in Buenos Aires, and everyone's invited. So if you want to present a paper, start writing it now, number one. And second, please confirm as soon as possible when or if you plan to attend, okay? Okay, let me get that one out of the way. Doesn't want to go away. Okay. And then the issue came up over the weekend, really, and it was carried out in the last couple of days as well. Today it was followed up as well, and that's on the issue of galaxies. The question was put up there by someone, a member of the Rational Science Group, and he says, "How are galaxies made?" And that created quite a stir.
Did we ask that once in one of the?
I think we did, but maybe we gotta go a little deeper in there. By the way, that's not God. That's the voice of my son, and he is kind of like God to me, but just you'll hear him in the background. Anyways, yeah.
My son.
we did discuss that, and we've discussed it so many times that we kind of forget, when we did it and how we did it. So there's no problem. We can cover the subject again.
So the question is, how are galaxies formed?
Yeah, the question is, how are galaxies formed? And there's a lot of parts to this. First, we need to know what a galaxy is. What is a galaxy? And we have to familiarize ourselves whenever we discuss these subjects with the galaxy rotation problem, with its relationship to dark matter, how the establishment explains black holes within a galaxy. It has a bearing on how we explain it with a rope. I'm proposing that it's got to do with a galactic issue, which is the galactic magnetic field, and I'll cover that in a second. And so these are issues that should be brought in there, okay, because they're all related. It's not just a question of how does a galaxy form. It's a little more involved than that. The official version is that we have Big Bang happening 13 billion years ago, 13.7. They keep changing or revising those numbers. And sometime later, first the atoms were formed, then gases, compounds, etc. Eventually we end up with stars and galaxies. Okay, so that's in a nutshell how the establishment explains the arrival of galaxies. Under the rope hypothesis, matter cannot be created from the void. Matter cannot turn into void. So atoms cannot turn into space, and space cannot turn into atoms. What does that mean? Well, that gives us a very interesting scenario. It says that the universe is eternal in both directions of time. It had no beginning, it had no end.
What do you mean by the universe?
Yeah, okay, the universe, right. We use the word universe. It's a concept because it involves both matter and space. And so there's a tendency of saying, talking about the universe when we should really be referring to matter and or space. If we say and, we're talking about the universe as a concept. If we say or, then are we talking about the creation of space, or how did space come into being? Or how did matter come into being? Which one are we referring to? Well, what happens is that in mathematical physics, they kind of bundle those two up in one thing. They say the universe, Big Bang, space-time, whatever they want to call it. They kind of put them together. They put matter and space together, and they consider space to be a physical object. So yes, you can create physical objects under that notion of space.
But when you say this, that the universe is eternal, you mean the matter within space.
Right, and again, what we're saying here is that matter is eternal. Space is eternal only in the other sense, in the sense that there is no such thing as space. Space is nothing. And the only problem we had throughout history is that we never defined the word nothing. We don't know what the definition of nothing is, what space is, what vacuum is. We don't know what the definition of that is. No one has put forth a scientific definition, one that we can use consistently.
Is it always defined in the negative?
Sometimes, yeah, it's nothing, no thing, nothing, you know. But that's, you can't define the nothing, because a cat is not a horse. Yeah, of course. It's also not a dog, and not a chimp, and not a tree, and not a rock, you know. So what are we going to use? All the words in the dictionary and find out what it not is? No, we got to find out what it is. We need a definition, and a negative is not a good definition. So space is nothing. And the definition of space, the definition of nothing, the definition of vacuum, these are all synonyms. Emptiness, you can use void. So many synonyms out there. Zero in mathematics. All these say that there is no shape. That's what space is. Space is that which has no shape. It's a concept, and it is distinguished from objects, things, entities, substances, all these other synonyms which have the opposite definition. It's an antonym, and the antonym is that which has shape. So we have that which has shape, that which has shape, it's a tongue twister, and that which doesn't have shape. So now we use these consistently. When we refer to space, no shape. When we refer to objects, shape. And so Big Bang, the creationist theory that we have today under mathematical physics, says that there was energy hidden out there. Energy is like God. It's a word of spirit that we put in there, because what is energy? How was it created? Well, they never answer that question. They just say we have positive and negative energy. We put them together and we have nothing. But when we separate them, we have something. We have gravity and we have mass. And the mass part is the objects. Okay, so that's essentially the story. That's the official story today. And so that's how the universe got created. From there you got the particles. From there you got the atoms, molecules, objects such cosmic celestial objects such as planets and stars, and eventually, you know, galaxies, which seem to be the largest structure that we can call structure up there in the cosmos. And so the question here is that that's what a galaxy is, but it's important to know how a galaxy looks. So here, let me put a galaxy here so that we can see it. And here we can see a galaxy, and it's rotating. Okay, it's a spiral galaxy in this case. It's rotating.
Are they all spiral galaxies?
No. The Magellanic clouds here, the Magellanic galaxies, they're really squarish. And I have the impression, I don't know, I'd have to research that, what the theory is today, but I have the idea that they were formed maybe by some collision of two galaxies. Maybe that's how they ended up like that. I don't know what the theory is.
It's their first day on the job. They haven't spiraled yet.
Yeah, well, they kind of rotate around the Milky Way. They're kind of on the periphery, but they're like if this is our disk, they're like that. You know, let me see here. Here. So if this is our disk, our flat disk, the Magellanic galaxies stand at a 90-degree angle, like a sheet of paper that is facing us. It's probably rotating in this direction, 90 degrees to us. I don't know about this. I'm just speculating here, and I don't know what the theory is for the creation of how they ended up like that. But then the question is, you know, how does this galaxy get created? But the important part here that we cannot see in that little picture of a rotating galaxy is the official version that says we got a problem what we're staring at right there. And the problem is that the outside, as you can see, the whole galaxy rotates as a single mass, single block.
Like a disk.
Yeah, like if it was all one piece.
Yeah.
And that's prohibited by Newton's law and Einstein's field equations as well. What we should be seeing is that the stars on the outside should go slower and slower and slower and fall behind the stars on the inside. That's not the case. In fact, here I have the curve. This is the dark matter curve. Okay, it looks something like that. Let me expand it a little bit. You see what the predicted values for the speeds of stars as we get farther and farther away from the center of a galaxy. So if you move farther away from the center of a galaxy, the way it should be, what the equations predict is that the stars farther and farther out should travel slower and slower and slower, like, you know, Pluto travels slower than Mercury. Why? Because Mercury is going around real fast around the sun, 88 days, and it does one twirl, one revolution, whereas Pluto takes 243 years to go around.
It's like, is that like the marathon runners or these...
Zeno's paradox or what?
No, runners at the Olympics where the people on the outside
yeah, correct.
have that head start to make up for the fact that they're on the outside.
Yeah. In other words, the tracks are specifically made in such a way so that you don't get the inside track, as it's called. That goes for horses. That goes for you know, when you're running down the track, you don't want to have an advantage. And the guy on the inside, the guy who's got the inside track, he has an advantage.
He essentially has the smallest track to run.
Right. He's got less distance to run, and that's the case here. The stars that are on the inside, they can supposedly twirl around the center of the galaxy faster than the guys on the outside. Well, that is not the case. What they've noticed when they look at galaxies out there and they've measured these distances and so on, and they, you know, these things don't move very fast from our point of view. They're very slow, but they can still see some motion. They track that motion. They say, well, this guy's moving fast or faster. As you can see the graph, the observed graph there, the observed part of the graph. As you go out, they go even faster. How can this possibly be? You know, they should go slower because the guys on the inside track, as you can see, the curve drops drastically as you get to the center. So the guys on the center are going very slow comparison to the guys on the outside. They have very, you know, we're talking about speed here. These guys on the outside are going very, very fast, much faster than the guys on the inside. And that's a no-no. How do you explain that? Well, they did explain it in their mathematical way. What they did is they sprinkled kilograms all around it. Okay, that's what they did.
All around what?
Well, they sprinkled around the galaxy, especially on the outside of the galaxy. In other words, they put more mass on the outside of the galaxy than they did on the inside. And I put the word kilogram there in, you know, the symbol because that's essentially what it is. What they've done is say, well, there's got to be mass here. What is mass? Well, mass is kilograms, right? And maybe that explains why it's invisible, because we can't see a kilogram. I can't draw a kilogram, never did. I can only draw the symbol there. And so they just sprinkled kilograms mass on the outside, and they say, oh, now the equation works. Oh, no kidding.
Why does the equation work when you have kilograms on the outside? Wouldn't that slow the outside of it?
No, you need the mass out there to make it go for to really have that swing, you know. It's got to have that weight out there to really make the stars go faster.
You'd think weight would make them slower.
No, it's like you need a mass pulling on the outside of these things, like to pull it in to make it go faster. You need to hold in essentially, you know, there is another part here that you need more mass that keeps the stars on the outside like together, like tied to each other, like you need that.
Okay.
If you have more separation between them, less mass, you got to fill that. If you fill that with mass, then now you can at least find out why this guy is attracted to that star, which is attracted to that other star, because now you got a mass in between them. And that's what they've had in their equation to explain the speed around, for the stars on the outside around the galaxy. They had to sprinkle mass.
I still don't understand why how kilograms make it go faster.
Well, it's this. Think of it this way. It's more like turning the stars on the outside into a carousel, into a platform, such that they all rotate together, which is essentially what we're going to suggest in a minute. But this is the issue. If you have a star, as you go out, the stars are farther away from each other. The distances between them are greater, so there's less mass between them.
Yeah.
So they should go slower, right? Because if you twirl a stone around your head or a ball around your head, if you twirl that, the farther this is, the longer you make the string, the slower this goes, okay? Mm-hmm. So we can all understand that much, right?
Yeah.
But now what if you have this ball on the outside, I'm going to make the string as long as I can within the screen, right? So here's where is it? Here we have the ball on the string, right? And there's another one over here, and there's another one over here, and there's another one over here, right? But the distances between them are great because they're way on the outside.
Yeah.
So now what if we fill the vacuum between the stars with some unseen kilogram matter or whatever you want, dark matter? You put kilograms, you put masses in between them. Mm-hmm. Now this one pulls on this one, mm-hmm. and this one pulls on the other one. Now they all pull on each other, and they all function as a whole wheel that's turning. And that's how they get this done in the equation, essentially. And I have no objection to what they're trying to do because we're going to do it the same way. We're just not going to use this monster called kilogram, this spirit, okay? So what's next? Well, what do I have here? This is our explanation, and it's done with the ropes. And what you're seeing there is a spider web. Now, I think all of you have seen a spider web, know what one is, and that's what you're looking at. What I did was, that's a spider web that you're seeing there, and now it's turning into all these little yellow colors, which I'm putting in there, which are the stars. Okay, so I'm saying that a galaxy, as seen from above, okay, shows a spider web, and all these stars are connected. They are connected between them. They form these concentric circles, and all these stars are tied to each other through ropes. Now, as you understand, if you've seen my videos there, and maybe for those who haven't, we have a coaxial between stars, because if you get close to a star, every atom is connected to you. So the closer you get to the star, the more the ropes fan out. The closer you get to its center, the ropes that come from the edges of the atoms that are on the edges come from wider and wider angles.
So the less they act as one singular rope.
Right. But this is the point. The point is that as we get farther and farther away from the star, all the ropes tend to get into form a coaxial, and that's essentially what's going to unite from one star to the other. Most of that distance is going to be a coaxial, a single straight line coaxial. And only when you get to the star, you get into what I call the bird's beak. If you look at a bird's beak, it's got this format where it opens up, and that happens near the star. But between stars, most of that distance is covered by a coaxial, where all the ropes are there. And I'm saying that each one of these lines that you see there, and obviously I didn't draw the billions of stars in our galaxy, but you can get the idea there. All these stars are connected, not only to the center stars, but to the ones on the sides by coaxials. And those little lines that you see there in the spider web, those are the coaxials. So I'm saying that essentially, a galaxy is a rotating spider's web. Okay? Understood?
Well, the difference in this case would be that here you have the lines of going out from the center, they're straight, but I'm assuming with a galaxy, since it spins, it gets this kind of whiplash effect, so it looks more like a tendril or a tentacle instead of a straight line.
Yeah, I'll get into that as well. I think I need to cover that subject as well. But the point that I'm trying to make here, that if all atoms in the universe are interconnected, then that means that all atoms from all stars in our galaxy are interconnected. And after you leave the star, after you leave the bird's beak, you get into this linear region, which is a coaxial, essentially, of all these ropes. And that's what this graph is, this picture is showing. It's showing that all the stars are interconnected, and they're not only connected towards the center, to the stars in the center, because all stars, all atoms are interconnected, but they're also connected to the side. And again, in between all this, you got a lot of interstitial gas. That means that you have atoms which also fill in the vacuum there, and who knows, there's planets, maybe rocks like asteroids, comets, who knows what kind of junk there is between the stars. There's interstellar gas, and there's galactic gas, and for sure there's got to be all kinds of rocks and stones, debris, just filling a lot of this space that we don't see because they're dark, obviously. You know, we can only see the stars. So this whole thing, the point here is that this whole thing is you should see it as a platform, as a carousel. It's a single platform, and it's rotating as a single piece. Now, is it perfect? No, in the sense that maybe some stars fall behind for different reasons, and maybe that's why they form some of these spiral galaxies. You know, you don't see perfect circles. Even elliptical galaxies are elliptical. They rotate, but they're not perfect circles. Mm-hmm. Then you have elliptical galaxy. You have there's all kinds of shapes up there. The most common being the elliptical galaxy. Okay, so what happens with this? Well, if we take this, let's put it in motion. We're going to put this, wrong one. Where do I have that one? Is the wrong one? Should be this one, sorry. So we're going to put the spider web. We're going to put it on top of the galaxy, and while the galaxy is rotating. And what we're staring at there is that all the stars are interconnected. That's what that picture or that GIF there is trying to show you. All the stars are interconnected, so when it twirls around, you know, there's no reason for any of the stars to be slung out of the galaxy. Okay, I think that's also quite well understood there. And so now let's move on to this one. Where is it? This one. Here it is. We superimpose upon that twirling galaxy, I'm going to superimpose on it the galactic magnetic field. And this is the question that raised so many questions. This is the issue that raised so many questions, okay? You can see how I drew it, how I illustrated this. I'm saying that the magnetic field of the galaxy extends far beyond the edges of the galaxy boundary of what we see of a galaxy. Maybe there's a couple stars out there as well that we don't see, or too faint or whatever. But the magnetic field extends way beyond this. And in this case, I have the magnetic field going in. I'll call that the South Pole, because when it comes in, it's the South Pole. When it comes out, it's the North Pole of a magnet. So this magnet has the North Pole facing down, the South Pole going up. We can turn it around if you feel more comfortable. And what do we call those regions next to the center that are spitting out all these, whatever thing that you see there? They call them jets. And they say those jets are being spit out by black holes in the center of the galaxy. That's the official version. So right at the bottom, not at the top, but at the bottom, as you go, where it's being spit out, where the spring is throwing out the water, okay? Those are called jets. That's what they named them, and they say those are caused by black holes. Black holes that, rather than suck in, spit out matter. Yeah, and you try to figure that one out, because we thought that black holes don't even emit light, but when they have to explain something, they'll twist everything around and they'll justify it mathematically. In this case, we have the jets on the bottom, they're being spit out, and for some reason they come on the top and go inwards. Well, what we're saying here is that all those lines that you're seeing are really, you're supposed to see them as threads. Countless threads being swung around, and which have their origins in stars. So the stars are swinging the threads around. The threads go around the galaxy, come in to the South Pole, which is up in the upper part, come in through the South Pole, exit the North Pole. Okay, so that's what we're staring at there. These are threads that are going around. Okay, and I'm saying that the threads help maintain the integrity of a galaxy. Not only are all the stars interconnected with these coaxials, and that allows us to rotate the galaxy as one piece, but to keep the integrity, or to add to the integrity of the galaxy, we also have the magnetic field. Okay? And so the question comes up, Dan asks the question, he says, what the hell do we need the magnetic field for? I mean, it seems like it's too weak, it's far-fetched, hard to believe. Let me use his words here. Where is he? Here he is. Here is his word. He says, if I said I was wholly satisfied, I would be lying. So he's not satisfied with my picture there. He doesn't like it. Okay, good. And what is his objection? Well, he says here, let me get one of these out of the way. He says here, if the sun were the size of a pea, the magnetic field would be about 100 meters away. Our nearest star, Proxima Centauri, would be 121 miles away. So on this scale, the Milky Way would be just over 3 million miles wide. Okay? So P, you know, what is it? The first one was 100 meters away. That's the magnetic field. Then we have Proxima Centauri 121 miles away, and the entire galaxy Milky Way 3 million miles away in this scale, on the scale of the P. Okay. He says, he continues, if magnetic fields are made up of sweeping walls of thread, which is what I'm proposing here, even a tiny magnet has far too many loose sweeping threads to ever count or even calculate. So galactic sweeping threads would have to be comprised of many, many more walls of thread. My intuition tells me, as I visualize the galactic magnetic fields, it would be far weaker given the distances between the stars. Are they strong enough to produce the phenomena? Maybe, but I'm not wholly satisfied.
Produce which phenomena? Okay,
the phenomena of, the question is the strength of the field. Magnetic field, is it strong? You know, how strong is it? I mean, does it have the ability to move a star? Does it a galactic magnetic field, right? Does it have that ability? Or is the magnetic field just sweeping by and causing minor, I don't know, effects? That's the issue. How strong is the magnetic field? And I'm saying it's strong, and Dan is questioning that. He's saying that, well, you know, if it's strong, you know, it's very hard to believe that, you know, you would have to have quite a bunch of walls of these threads sweeping down for it to be strong. And one is that, but I'll just clarify something there. You don't need to have tons, you need to have lots, obviously, of walls, but remember the walls are one right after another, so you have a block of walls. It's like constantly sweeping. It's not like one wall sweeps and then the other one sweeps later, 2 hours later. No, it's like it's a constant sweeping of walls that are pushing down on the stars. That's the first one. It's a flow. It's a flow. It's a wave. Okay, that's the first. We have to keep that in mind. Okay, okay. But anyways, this is a solution that Dan gives us. He says, what if, you know, if the galactic magnetic field is very weak, would it be more plausible to assume dark objects like huge, highly compressed planets that have higher gravitational pull, or massive iron planets that are cool but still have a strong magnetic attraction like a giant magnet? Maybe even planets made of neodymium, iron, and boron. Maybe it's a mix of all this stuff. And I clarified to him today that, you know, I don't think there are massive, rocky celestial objects out there in the universe, in the entire universe. Anything that's big is gas. Okay? There's no rocky stone up there monster that exceeds, like, I don't know, I was thinking of Betelgeuse, one of the biggest stars, or Antares, or any of those big stars.
Won't those be rocky once it goes out?
I don't think you can form it, let alone that it exists, but I don't think you can form it because the issue is that take a big star, a sun, right? And it's burning its fuel over time. It's converting lighter elements into heavier elements. And let's just say, well, it even makes uranium in its center, okay, or whatever.
You got a huge rock.
Yeah, you got a big, big gas ball that, is so big that it has the pressures necessary to create uranium or any of the radioactive elements, the higher elements that we see in the periodic table, and it can create those, let's say, in its center. Okay, so now this star explodes, okay? Supposedly it, according to relativity, it shrinks to a black hole, but let's say this star explodes, right? And it leaves behind this rocky planet. How big can that thing be? And again, we're talking about a star that has all this matter, this gaseous matter, to begin with. You got to have this big ball of gas to begin the process. You can't just start with a small ball of gas and expect to get, very high, heavy elements in there. So you need to start with a lot of gas. And, the largest stars we found, stars like Betelgeuse, and there's like 3 or 4 even bigger than those, but I don't think they have the mass, the amount of matter to be able to shrink inside.
I saw a documentary where they were comparing suns or stars, and they had this one, what was it, Canis Major or something?
Yeah, Canis Major.
Enormous.
Yeah, but again, a lot of these are bloated.
Making atoms in the center of it that we can't even imagine.
I think that a lot of these also keep in mind something else. First, they're very uncommon.
Yeah,
okay? That's the first one. So if there are stars that are big, they're very uncommon. Second, a lot of these are bloated, they're paper tigers. There's nothing in them. They're like bloated balls of gas, but I'm not sure they're compact completely in the sense that they have, I think they're not dense. I don't know. I have this idea that if they're so bloated, maybe they're not fully dense. And again, that's my vision of this. But again, there's not too many of them, so I don't think that for any given galaxy you would find so many of those that would produce the effect that Dan is talking about here.
What effect is he talking about?
Well, he's saying that what if we have some heavy iron or heavy elements, some rocky planets, because we're saying that planets are black dwarfs, essentially cinders of stars. Okay, that's what they are. And I don't think we can find a cinder of a star, a black dwarf, that is as big as Betelgeuse or Antares or any of these big stars. I don't think you'll find such a major big block of stone out there. I don't think that's the case. But assuming you could, I don't think they're very numerous. And if they're not numerous, you still wouldn't be able to produce what Dan is suggesting here, which is maybe this object is there and it's got a strong magnetic field and it's also got a strong gravity because it's got so much mass, and maybe that's producing some funny effects out there. My gut feeling is no. Okay, but that's my opinion. That's my gut feeling only. And again, I base it only on the fact that I don't think a star can collapse to such an enormous object. In fact, I would have doubts if there's anything big out there, a planet that is a solid planet, a rocky planet that is as big as Jupiter. But yeah, there could be. I don't know. But we don't have that experience. We don't really know. We haven't seen one out there. And more so, we'll probably never see one because every time we look at an object, it's got to be shiny. And usually it's because it has its own light. And if it's Jupiter, maybe it could have, or a little bigger, it could have its own light. But then again, it would indicate that it's a gaseous planet and not a rocky planet. Rocky planet can only reflect light from its own sun, and that light is too faint to reach our eyes. So I don't think as far as I know, we haven't discovered any. Not big rocky planets. If we saw a planet out there, it's more than likely. If it's big, it's like Jupiter. It's a gaseous ball. And if it's small and we saw it, we just saw its reflection because the sun or its star was there, it's got to be small. And so I have a lot of doubts about this solution. But again, it's one of those things that I'm suggesting people go out there, do a little bit of research, maybe present a paper for the Argentine conference. And let me continue here with, so we don't leave him aside, here's Dave. And he came in with a question also, and he says, after I looked at or explained more detail what I was suggesting as far as how the coaxials spin the threads around themselves, because this is the suggestion. Suggestion is if the coaxials are uniting any two stars, right, then conceivably if they're spinning, and we have to get the threads for the galactic field somewhere, and I'm saying we're getting them from that coaxial. Some of the threads pull out of there and are swung around. And those are the ones that are going to contribute to the magnetic field of the entire galaxy. So if we look at it as a ring of stars around the center of the galaxy, and another ring, we have all these concentric rings of stars, right? And they're swinging their threads around. Well, these threads are the ones that are going to eventually form the magnetic field of the entire galaxy. That's my scenario. So based on that, Dave says, does this imply something like a column of atoms within each star, as in maybe a cylindrical column right through the center of each star, oriented in the same direction as the stellar bar magnets? So here we have all these stars, and my gut feeling is that all of them, if not most of them, are aligned with the magnetic field of the galaxy, because the galaxy compels them to align in a certain way, just like a magnet compels iron filings to align in a certain way. So it kind of magnetizes them because it's orienting them, and I think the magnetic field of the entire galaxy does something similar. It spins around the galaxy and sweeps through the stars, and like maybe buoys in the ocean, they're kind of like this, and the magnetic field sweeps them and kind of forces them to align in a given way. And so I think the magnetic fields of all the stars are probably aligned in the same direction, and because they contribute to the magnetic field of the galaxy, that also forces them to align in the same direction. So I think it's just like unavoidable for all these stars to spin in the same direction.
Are the magnetic fields of the galaxies too big to affect the smaller things here on Earth, or else why wouldn't all metal on Earth be magnetic?
Okay.
It would become magnetized by this cosmic.
Okay, let me get to. I'll get to that. I think I'm going to answer that question together with a couple of issues that I'm going to be bringing up. Okay. So let me just finish what Dave said here, with threads spinning perpendicular to the coaxial connection between the stars. So again, let me repeat. We have a coaxial that unites two stars, right? And within that coaxial, some of the threads come out because the stars are spinning also in some way, or at least they spin the threads for some reason. The thread is spinning. That's going to be the magnetic field that is between two stars, and that magnetic field contributes to the magnetic field of the entire galaxy. And again, the only way we can visualize this is if it's a ring and the threads go in the ring perpendicular to the ring. So the threads now come down the ring, where we're going to do it like I showed it there, with a south pole at the top. The south pole at the top, north pole at the bottom. So the threads come through the middle of the ring, come out, and then come back out, and keep doing that cycle. Okay, who knows how many millions of years all these threads take to go around. But I think if we had God's eyes, what we would see is that the galaxy is not only comprised of coaxials that tie or that bind stars, but that between each star, that coaxial releases threads that contribute to the magnetic field of the entire galaxy. And these two phenomena, or especially the second phenomenon, is helps, not only contributes to the number of threads that are swinging around, but it also forces the stars to align in a given direction within the galaxy. There is a possibility, which has occurred to me, that maybe, and I'll get to that in 1 second here, that since I maintain that the magnetic field of the stars, of the galaxy, is what compels the phenomenon we know as black hole, the star swinging around nothing or losing gas to a neighbor or whatever, it's very possible that that star is not aligned like all the others. And that's why the magnetic field of the galaxy picks on that little star and says, we're going to turn you around. You know, you got to have the right position just like the other. We're going to make you fall in line. And if it's sideways or maybe in a different direction, maybe that's one of the reasons that those stars are spinning in a given way, because until they are aligned properly with like the rest of the stars in the galaxy. That's one possibility. But let's get to that. Let me just, because I want to answer your question with that as well. Okay. And that's, here is what people observe. Here we see a star that's revolving around nothing, okay? And so they say, well, why would that star go around nothing? And the solution is always kilograms. You know, it's always put mass in there and you'll fix the problem.
There's a really heavy black hole there.
Yeah, what they do is they have to put mass in the equation to explain that phenomenon. And if you put mass, then you got to explain that mass. And they say, well, where does this mass come from? Did God just put it in there? No. And they say, well, no, we can understand this very easy. You know, a big star collapses to a point. It disappears. There's no structure, but the mass remains. The elephant's gone, but his mass stays. And now the ant goes around the elephant, or whatever's left of the elephant is his mass. And that's what you see here. You have a star that's revolving around nothing, because in the center of that, you know, in that nothingness, there is a black hole. There is mass, but no object, no structure, no substance. Black hole is said to crush matter out of existence. So there is no matter. There's only mass. So mass is not matter. Mass is simply a mathematical parameter that we put in there, like saying there's a lot of weight. So much weight it's bending space in that area, and the poor little star has no place to go except around it. Okay.
What's really happening?
Okay, and well, there's one more step here, and that's the other one. The other phenomenon they observe is this, and that is that what they observe is on the left. What they put in by hand is on the right. And what they're saying is, look, what we notice is some stars are losing gases from their surface, copious amounts of gas, and we don't understand what could be causing such a phenomena. And then they say, oh, we know. What's happening here is that there's a black hole nearby just sucking the gases out of it. So they use the black hole for not only to explain why a star revolves around nothing, there's a revolution, an orbit around nothing, but also why a star loses gas from its skin. Okay, both things. So how do we explain with the rope hypothesis? How do we explain black holes? Well, the black hole, we begin with a phenomenon that we find on Earth, and that is that a ball, a charged ball, we'll call it a charge. I hate that word, but it's a convenient word when you're discussing. There's a ball that's electrically or magnetically charged, okay? And so it spins around in a magnetic field. And as you can see, it's spinning around nothing. There is no physical object in the center. That whole revolution is done completely by the magnetic field, okay? And so we can produce this effect here on Earth. I'm not going to show it here, but we also have that a magnetic field can pull smoke. You light up a cigarette or have a little bit of smoke, and the magnetic field, you have a magnetic field generator, it pulls the gas right in.
What? I want to see that.
Yeah, I've got a picture of that. I got that on a video, but I didn't put it up here. Anyways, those two effects we can produce here on Earth, and we do them with magnetic fields. We don't do them with black holes, okay? And that's important. So here is the explanation. Here you will see, I hope you can see it, there's a little dot that I put in there, and that's supposedly the star that's moving around in circles. And it does so, here I pointed it out with a red arrow. And that's caused completely, as far as I'm concerned, it's caused strictly by the magnetic field of the galaxy. So we have, at least that's the explanation that I come up with under the rope model. If you have a better explanation, specifically I give that question to Dan, please be my guest. That's my explanation. Let me make this one smaller here, whatever this is. Um, so that's my explanation for this. I'm saying that magnetic field causes the star, which also has a magnetic field. So you have a magnetic field ball within the magnetic field of the galaxy, and that's what's twirling it around. Just like the ball did here. One more, I'll put that up there one more time. Here you can see the ball rolling around, orbiting nothing, only due to the magnetic field. We have this effect here on Earth, and this one is the galactic phenomena under the same conditions. We're seeing the magnetic field is sweeping down and forcing that charged object, the star, which has a magnetic field, to move in circles around nothing. And likewise, I think I have it here. Oh no, this is just the side view of that same thing. You can see the threads coming down, and we have the star in question that is twirling around in a circle simply because the threads are coming down, are sweeping across that charged object, celestial object. Okay, so that's the explanation, and we have to be able to explain this type of phenomenon because it's something that's already been registered out there. They have observed the stars going around in circles around nothing. They see there's nothing there. They also have observed stars losing gas. We can't say, well, that doesn't exist. That never happened. We can't say that. We got to explain it, and the rope model explains both of them quite well. If this is the only explanation, then yes, the magnetic field is strong then, because it has the ability to move a charged object. Now, the question that my son asked here, does that same galactic magnetic field have the ability to move something like the moon? Well, the moon doesn't have a magnetic field.
That wasn't my question.
No, hold it, but I'll get to it. But I'm starting slowly here.
Okay.
I'm saying the moon doesn't have a magnetic field. I don't think it has a noticeable one, or at least, or maybe it doesn't have one at all. But if anything, I would say that the magnetic field of the galaxy that sweeps right through the moon probably has very little effect on the moon, or none, or none that is mention of worthy of mention. Does it affect the Earth? Because the Earth does have a magnetic field.
Yeah, the moon has one. It's really weak, though.
It's weak? Yeah, I figured it probably had one. The Earth has a stronger magnetic field, and out of the rocky planets, it's got the biggest magnetic field. But you could even take Jupiter, which is much larger than the Earth and has a bigger magnetic field than the Earth. Does the galactic field affect Jupiter? Well, maybe not in any significant way, because something else. And that's that you have the sheath protecting the entire solar system, which is the magnetic field of the sun. The sun has a magnetic field that extends way beyond Pluto, beyond the Oort clouds, I think also, as far as I'm concerned. It extends very far out there. It forms part of the, what is it called? The shock? Galactic shock. No, not galactic. The solar shock. I forget the term now, but it goes all the way to where the sun, or the entire sun system, solar system, meets interstellar space, or interstellar debris, or interstellar galactic field. Okay, sweeping in that region. So the sun has its own magnetic field, and it protects the entire solar system from any outside interference. If there is a galactic field sweeping down, we're protected to a great degree by the sun's magnetic field. Likewise, we have the Earth has its own magnetic field, and it protects us from the sun's magnetic field. Everybody's got his own force field protecting. Everybody's got his own force field, and we're all being protected properly. Fortunately, God, provided for all of us. The Earth has its magnetic field, and even though the magnetic field of the sun sweeps right through us, it doesn't affect us that much because of that protection. We are also protected thanks to the magnetic field, the magnetosphere, as it's called, that covers the Earth. We're protected from the solar radiation, from the the debris coming from the sun, the solar wind. So we're protected in many ways, not only by our sun, but by our own magnetic field, but the sun protects us from the galactic or interstellar magnetic field. So I think that's one of the reasons we do not suffer the ravages of the galactic magnetic field. But that doesn't exempt a star that, again, maybe could be misaligned with respect to other stars. And maybe that's why the galactic magnetic field is punishing it and saying, we're going to force you to align, to fall in line with all the other stars. And meanwhile, this guy's maybe tilted or maybe at a different angle than the magnetic field. And maybe that's why it's being forced to rotate around nothing until it finally, you know, after maybe, who knows, a few million years, it finally, you know, it stands in the same direction as all the other stars, at least all the other stars nearby. So that's my gut feeling. But again, like I suggested to Dave today, you know, go out there, write a paper. You got a subject there. It's an interesting subject. You're welcome to consult me. I'll pitch in whatever I can, whatever, you know, comes to my mind, and present it at the Buenos Aires conference. How's that? Okay?
Time to start questions.
Now for the questions.
50 minutes in.
So let me get all this stuff out of here. Where am I? I lost myself.
So we have our own force field.
Yeah, we have our force field, and that fortunately protects us from all these evil spirits that sweep across us. No questions today?
Yeah.
Oh, okay, good.
Well, let's start with since we're on galaxies. This was a question that I saw a lot in the documentaries, which is what is found between galaxies?
Well, you have interstellar dust, debris, you know, gases. It's very possible we don't see them, but maybe there are asteroids and comets. And the reason I think that is that, you know, outside the solar system proper, which ends in Pluto officially, if you go out there, you get to the Oort clouds, and they're like, you know, an asteroid belt that surrounds the solar system. And I'm sure if we go out there, stuff we can't see because it's too dark and there's no star out there, no sun or anything, and even the light from the sun is too dim to really make them shine. I would suggest that even between here and Alpha Centauri, the nearest star, there's probably more debris than what we imagine. Maybe there are gases, interstellar gases out there. Who knows what's out there? We don't see it because I don't think we'll ever be able to see something like that. It doesn't have its own proper light. It doesn't reflect the light from the sun or from Alpha Centauri. But who knows? Maybe between the stars there's a lot of garbage.
Wouldn't all that garbage or dust that you're talking about have been sucked in by one of the galaxies by now?
Maybe, because again, keep in mind that even though the sun rotates quite fast, every 11 hours, one turn. So faster than the Earth. We take 24 hours to turn. The sun does it 3 times, almost, well, more than twice as fast.
I know that.
Yeah. So so the sun twirls quite fast, and it's a bigger ball than us.
Yeah, way bigger.
Yeah. So I mean, we fall into the sun like a million times, just to give you a relation there. And so, you know, the sun twirls quite fast, spins quite fast on its axis, and the question is, what effect does that have, like on something like the Oort cloud or whatever debris is out there beyond the Oort cloud? And I'm saying that the farther away you go, there's less gravity, and so I don't think those things are affected either by light or by gravity as much as we are. For example, we're essentially stuck to the surface of the sun. We don't think that way because we're 8 light minutes away from the sun. These things are, you know, a little farther away. You're talking about not 8 light minutes. We're maybe talking about like days or weeks away from the sun. And the question is, does gravity have an effect that far out? And if light doesn't, because, you know, if you were standing on one of those rocks and you look at the sun, it looks like a little star out in the distance. And then likewise, you know, this guy will not reflect the light from the sun. So
We started-
I think there is debris out there. There are probably gases, and maybe they're kept out by the magnetic field of the sun also. But and that also tends to make it less effective in influencing those things into coming in.
So they're more stranded.
Yeah, I think they're out there like floating in nothingness, and they're more or less static. Maybe they orbit the sun to some degree because there's a loose gravity there, and the spinning of the sun maybe does move them around a little bit. But I think it's not by no means what we see in Galactic. On the outer side of the galaxy, you know, this rotation in the stars, they're bound to the ones on the inside twirl just as fast. And the reason for that, again, is that, you know, Pluto is connected to the Earth, which is connected to Jupiter, which is connected to Venus, and we're all connected. But there's no matter there. It's so low density that that the same effect that we see in a galaxy, we don't see it within the solar system, where all the planets travel like a, you know, carousel all around. We don't have that much matter to produce that. That's why they had to put matter on the outside of the galaxy.
We started the conversation with a question that still hasn't been answered. How are galaxies formed?
Okay, yeah, now that we got an idea of how a galaxy is structured, at least from the rope model, you know, that they're all the stars are interconnected, and we have the sweeping magnetic field that helps continue maintain the integrity of the galaxy, and at the same time can explain black hole phenomena and also can explain dark matter. Now that we have that picture, let's see if we can look at this in the following way. Like I said at the beginning, you know, matter was never created, and I don't think it'll ever be destroyed. If anything, it converts into something else. Galaxies have always been there, and while one galaxy might destroy itself, maybe by colliding with another galaxy, because they eventually come near to each other and there's some effect going on there. In fact, they've got pictures taken by, I think, the Galileo or one of those telescopes out there, where they see galaxies which are in the process of merging, colliding, blending, whatever you want to call it. Maybe they're just going through each other, and with all kinds of havoc happening in there, because you have a star that's going around the center, and suddenly you got these two guys going around the center. Let's see if I can get them in the center here, and they're going around the center, but they're approaching each other at some point, billions of years later, right? Some point, you know, there's got to be some influence, gravitational and magnetic influence between all these objects. And so what happens when two galaxies cross each other? Well, there's got to cause all kinds of problems. And it restructures a galaxy. Maybe the galaxy becomes bigger. Maybe the specific way in which the two galaxies met. Like, one thing is for the boundaries to touch each other, or very far, you know, just the edges of the galaxy to touch each other. Another one is for the centers of the two galaxies to come together. You know, they just happen to meet at the center, right? And so those different types of interaction produce different types of effects in galaxies. But let's look at the worst case scenario. Two galaxies come center to center. They collide face to face. Well, what would that effect do? Well, they've done computer simulations of that, and they've come up with all these different scenarios. And again, you know, you can believe anyone you want there, because they, you know, different people have different theories based on their simulations, and they come up with all these galaxies that could be formed or deformed from such collisions or interactions. But all we are doing really is not creating a galaxy in the sense of, you know, how did God create a galaxy from nothing? We're not talking about that. What we're talking about here is two existing galaxies colliding, interfacing, interacting in some way, and that process creates a new galaxy, which could be bigger, could be a part of the other galaxy. Maybe the other galaxy, like the Magellanic galaxies, we got two of them here, the small and the big one, and maybe they end up being part of our galaxy, like subsidiary. It's like a suburb to our galaxy that's floating or rotating around our galaxy, also because of gravitational and magnetic influences. who knows? All these are done with computer simulations, and there's tons of those. You just got to look them up. YouTube has quite a few of those. You just have to look at what those galaxies look like. But starting from scratch, saying, well, first we begin with one star, and then another one comes around, and another one, then they form a little group, and now they're all pals, and now they start rotating, more stars come in and join them. I don't think that ever happened. I don't think that's the way galaxies form. I think the way galaxies form is simply by interfacing, deforming, and reforming. That's, I think, the way it's done. And there's this eternal process of galaxies colliding at their scale and producing new galaxies. That's all it is.
There's no such thing as producing a galaxy. They're just all trading Pokemon cards.
All we're doing is...
They're all just trading atoms.
All we're doing, I think, is you can't create matter. All you can do is modify matter. You can transform matter. And I think what galaxies do is transform galaxies. That's all they do. Galaxies transform galaxies. What they do is they collide, they interface with other galaxies, then they deform and reform. And maybe a star that belonged to the other galaxy now belongs to this one for whatever reason, because of whatever interaction. Now this guy is a trader and he joins the other galaxy, and this one maybe pulls a couple of traders from the other galaxy. Maybe something like that. Who knows? I'm sure the computer simulations are something people should look at to get an answer to that. But no, God does not create galaxies from scratch, not in my opinion.
So I guess the question is wrong. It's not how galaxies are formed, it's how does matter go into that shape, or I guess it's just all matter just moving around. Well,
no, other than that, yeah, we have to give credit to gravity, because as even if two galaxies go through each other or collide or whatever, it's gravity which plays the gravitation, which plays the big role in there. It's what's going to, it's the masses pull in one direction or in another direction that produces certain effects. That's one. And the other one is that you have the magnetic field also, which contributes to that process in some way or another. So, yeah, we don't create galaxies from scratch. We simply modify existing galaxies in some way or another. And again, there are lots of computer simulations. You can look them up. But anyways, once again, anyone who has a better theory, please present it at the conference in Argentina, 10th of November. We'll see you there, and I'll see you tomorrow at the same time, same station.
Bye, guys.
Bye-bye.